is Huckabee Clock Talk, Random Clock Talk number 5, tape 5 by J.M. Huckabee. We're in the shop of the Huckabee shop on J.B. Ranch, just north of Austin, Texas. We're doing a little bit of clockwork and most everything that you could imagine here, and placing this on videotape. And the clock that we've been working on tape 4, we have sitting here is disassembled from the previous clock talk. And the thing I'm going to do is to go into something else that is a little deeper in the way of clockmaking. We look at this second wheel, nicely cut gear, beautiful pinion, very nicely polished, just about an idealistic gear. We're going to set this thing in the vise and tighten that up. I'm going to pick up this saw. I'm going to saw the pivot off this wheel. That seems to be a terrible thing to do to such a nice looking clock. But the thing I want to do is to go through the process of repivoting an arbor and show that this can be done and returned to a almost undetectable repair that goes into this. We'll go through all the stages. I neglected to see where the piece went when it popped off here. I should have saved that so that we could have it in the container there for a showpiece. Now, the thing we'll go after is how to set this up in the lathe. We'll make a lathe setup. We will cut off the burr that remains on this end. We will locate the absolute center. We will drill that to a depth up somewhere along here. We will make a new pivot, which we will press fit into that, finish it back to the original size, and we want to do this without distorting the appearance or the performance of this particular gear. That's going to be the object of this clock talk. This is one of the jobs that is required in the American Watchmakers Institute of certifying a clockmaker. This is one of the things that is required in the practical work in the certification examination. There are things that are more complex than this, but this is a job that every clockmaker has in his shop on a pretty regular basis. So this will be the thing that we're looking for. I'll cut the camera and make a setup on the lathe, and then we'll get going with it. We're ready to go on this job. Let's see how we're going to hold it in the lathe. We'll make a dimensional measurement on this section here. I believe I will not hold this on the wheel chuck. It would be very feasible to do that. But I have a nice cylindrical tang here. I think I'll hold on to that tang in the lathe. Measurement here says that's 120 thousandths of an inch, and that would bring us to a number 31 collet. I have to get down here with the eye loop to find this thing. This one. We'll slip this in the 31 collet. We find that this is just a good skin-tight fit. We set that into the headstock and slip this in here and give it a ring, tighten it up, and let's see how it runs. Let's turn that on and look at it. And to catch the tremor, you remember, if we want to catch the tremor, we can magnify it by going out onto the end of a rod. That is essentially perfect in where it's running. We might imagine that all we have to do is to go right in here and skin off this little bit of the pivot that remains, that we would locate the center, that we'd run a drill in it. And it's really not that simple. Here's the problem. If we lay into this with this great overhang out here, we may break this arbor off. We may break it off up in here, we may distort it, and that's just not the way to do it. We move our draw bolt down to this end of the lathe, and we get a study rest. See if we can find the study rest in here. The study rest says, oh, let's see what it says on it. It says R Flaming, F-L-A-M-I-N-G. This was purchased through some supply house. They're currently available. They're available in a variety of heights right in this region so that you can fit up whatever lathe you're in. And we'll pull the, well, we just dropped that pivot, that support. We'll slip this back not too far from the end. We want to support that arbor right out to the point where we're working. And the draw bolt on this doesn't have a very large knob on it. Most of the lathes that I have, over a period of time, I have made new handles for the draw bolts and can turn them very easily. That one I have to lay into a little bit hard. We pull this up till it touches. That's right here. We're pulling this prong up till it, probe up till it touches. We pull this one up till it touches, and we let this one down till it touches. Now that says that as that runs, it's not going anywhere. We put a drop of our favorite Red Dog lubricant on that, and now we have a support, and we want to be sure that it's not tight, and we're ready to go. We now have a support right up onto the end of the pivot. Let's see if we can get a little more light up here and possibly see that. Get this little high intensity light there. I'm afraid that the focus of the camera, and let's try touching the focus a little. That's the zoom, and let's see what we get. Looks like we can't do much better. Okay, and now I'm in a problem. I'm going to have to cut the camera a minute and locate my tool rest for this particular job. Oh, here it is. Thought it had gotten away from the bench. All right, we'll send this tool rest up pretty close up here. Now, one of the problems you have in this particular type of work is you cannot get the tool rest in close to the work, right here. The tool rest touches our study rest. Let's see if we can move this study rest over just a little bit to improve that situation. Be sure that we didn't get that into a bind. Come over here, we can get in a little closer. That will help us some right there. Get this tool in close. This particular tool rest may do me a little better if I can turn it around like this and get my clamping lever on the back side. All right. Let's see how hard this thing is. When I was sawing, I suddenly realized that that pivot was not exactly soft. So let's see what we can do on turning this. The thing we find on turning this pivot is that it is hard steel, but it is fairly free machining. Fairly free machining. I'm having good success in turning this back. And to discuss the technique that I'm using, I want to not cut into the shoulder. I don't want to shorten the shoulder of this arbor. So I cut almost to the shoulder, Then I formed the center, or began to form the center that will catch the drill that is going in there, and I need to deepen that center just a mite before we start running the drill. Let's see what we can do there. Now let's recall the technique that we were using on a previous tape. We said that we can take a very sharp scriber and set it in the center and feel of it, and if we can feel a tremor, we're not on center. If we can't feel a tremor, if we can't feel that part running, then we are dead on the central axis. I am dead true on that axis. There is no pip in the bottom of the center, or I would feel it. The end of the scriber would be looping. That's a test that you can make that's easier to detect by feel than it is by sight. Okay? Now we need to determine the size. We need to determine the size that we're going to make that pivot. Had I wanted to rig this demonstration in some way, I would have measured the pivot before I cut it off, and then I could have had that in my mind, but I didn't do that. So let's see what we do there. We'll use a drill to do that, and let me get the plate that this is associated with. Let's look at the plate. We find that in this situation, I'm in trouble getting back in the camera. Right here is the pivot hole we're talking about. That's where the pivot goes. Let's look at a drill index and find what that might be. I suppose it's in the order of possibly 75 thousandths of an inch. I don't know. Let's pull out a bit here that says 76 thousandths of an inch. See how it fits to that hole. Well, that's pretty close. It's pretty close, but the hole is smaller. The hole is smaller. I can't put the chucking shank of that bit in that hole. Let's back down another. This bit is 73 thousandths that we have, and that exactly fits that hole. That goes right in that hole. The chucking shank of it is 73 thousandths. Well, is that what we want to pivot? Let's measure this and be sure that we're okay here, and I'm measuring about 72.5 on that. So that gives me an idea of where I want to go. Suppose that in this situation that we just drill this with the 72 or 73 thousandths bit. The bit will over drill slightly, and that should give us a little space to finish out the pivot. So let's just use this bit for the purpose. Go over here in the toolbox and see if we can pick out something to hold this drill bit with. I frequently hold bits with a little pin vise. Get this bit in here, and well, that's not a pin vise. That's a little hand vise. I purchased that many years ago, and we'll prepare to drill. Let me cut this camera for a moment and look for another item or two. All right, we're back. The thing that I wanted to locate was my oil can, Alright, we'll put a drop of oil on this, and we'll see what we can do with the drill bit. I'm drilling this freehand. Now, remember this, the deeper we go, the more easy it is to get a good job. And so how deep do we go? I've looked through some literature that says that the pivot should be no less than 1 diameter deep, preferably 2 diameters deep. And it's my personal opinion that in repivoting, if you're only 2 diameters deep, it's very difficult to get a good job. I like to run these things about 4, 5, 6, 7 diameters deep. It's not all that big a deal in drilling. This is matter of fact, this particular pivot is not too hard to drill. The material is quite hard. It is quite hard, but it is free machining. These drill bits I have are very good, very sharp bits, and not a particular problem in doing it. The hole's going in very straight. I don't feel any tremor on the I feel no tremor whatsoever in the handle. Let's clean out the hole and take a measurement and see what it looks like. Well, I suppose a simple thing to measure the depth of that hole with is a broach. We'll slip a broach up in that hole and pull it out and look at it. The only problem is I don't think you can see that broach. Let me find a larger one. Here we go. If you can see that depth right there, let's see if I can get a measurement off of the vernier caliper here that'll give you an idea as to what that distance is. There we are. This says that we're 469 thousandths of an inch. That's pretty deep. 469 thousandths. 10 millimeters. 10 millimeters is around 400 thousandths. So you see that hole is like more than 10 millimeters deep. We have one intrinsic advantage that comes by default in this. Generally speaking, a drill bit will drill a hole that is larger at the entry than it is at the bottom. That is to our advantage when we start cutting something for a press fit. When we attempt to make a press fit in a hole, that can come to our advantage. We would like for that fit to be very, very tight, to never come out forever and forever, and for this job to be as perfect as the day it was made. I notice in the AWCI prospectus of the instruction of the things that's to be done in certification of clockmakers, it says that this job is to be done so perfectly that it is not readily detectable. That is a subjective situation, but that's the class of workmanship that we would like to go to, and that's the thing that we want to do right here. I want to break the mouth of that hole just ever so slightly with a graver. We'll pull this out, and then we'll start making the pivot. You see that drilling an arbor is not all that big a deal. The real problem is being dead on center. And to be dead on center, you need the study rest in the lathe to do it. All I want is just an ever so slight touch. I want to go back in with the drill bit to get the chips out, be sure that it's completely chip free. We'll cut off, and so much for that. Now that's not a difficult job. That's not a difficult job at all. There is many things that we do that is far more difficult to achieve than getting that pivot hole deep and dead on center. Set that aside, pull this out, and we'll look at this, and the jaws in this study rest are made of brass. They're relatively soft. You oil them well, you have a polished spot on this, and you say, what am I doing looking around sideways? I'm trying to see in the monitor, see whether or not we're there. But I cannot detect, I'm unable to detect where the jaws of that study rest supported this. And again, let's look at the depth of this. Maybe this dark drill bit would be more visible. The hole is that deep. Let's try it again. Right there. That deep. All right. We'll cut off here, and I'll make another setup or so, and we're continuing on the repivoting job. Let's look at this piece of rod here. This is a piece of drill rod that's moderately hard. We'll slip this in the lathe, saw off a piece of it. The piece is too long to place in the lathe because the whip on the outside of the headstock would be a problem if we drive this at high speed for polishing. This is 110 thousandths of an inch in diameter. That will take about a number 30 collet, so we'll have to change that. And look in the block here for a number 30. Number 30 feels a little bit loose for that. Let's try that. There we are. We're better. Okay. Pull up. Looks like this rod has a little bit of kink in it. The thing I want to do is to saw this off at this point, primarily to see how hard it is and about how free machining it is. This is approximately the same feel in the cut that I had when I was sawing off that pivot. So that's good news in itself. It says that we will be able to machine this readily, and not readily, but without too much difficulty. And in addition to that, we will have a pivot as hard as the original without any heat treatment on it. Let's look at this situation again. We'll take a file, we'll break the edge on that. I want to smooth that surface. Turn it around, get all the tarnish off of it, and then I will be able to go in and out of the collet and run true. Let's see what kind of success we got on running true here. Remember that we can hold something up close, look at the trimmer further back, and we are running quite true. All right. The indication of the depth of the hole that we were in is hole in the arbor was in the order of, I believe, 470 thousandths, or in that order, and so we'll need to turn a tang about that length. The diameter of this rod is 110 thousandths, so we have to pull that 110 down to about 75 thousandths, and then that will be press fit in there. see if we can find something that doesn't have a hole in it. See if we can find something that will go in this hole. This little scriber goes in that hole to about this point. Let's see what that measures there. And I'm measuring 73 thousandths, so that says the bit didn't over drill very much. All right, we'll slide this back into the chuck. We'll give it about a ½ inch of overhang here. We don't want too much overhang, because as we cut this smaller, it will become, it will flex more out at this end. All right, set up our tool height, and we'll get a tool bit. We better place a little oil on this hard projection and see what we can do with it. Let's try the sharpness of this one. I think that will do all right. Get the eye loop on. I keep referring to eye loop. Take my cap off again. Keep referring to eye loop, but again, this is the pair of safety glasses that I wear, and possibly you can see right up in this corner here is what I refer to as the eye loop. That is a lens for close-up viewing, much as a watchmaker would use, and it's cut into the glass of the pair of glasses. Now the thing I will do, I will work on the reduction of the stock out on the end first, and then work my way back to the headstock. That will leave strength in the parent piece as I'm doing the work. This is pretty hard. It's pretty hard. It's harder than the stock that we were drilling. It's harder than the arbor that we're going to place it into. Let's see what kind of dimension we have at this point. I am 90 thousandths. We're going for just over 70. Let the tool bit run under the stock then. Continuing to cut. Let's talk about the philosophy of the cut that we're to have. I'm looking for ever so slight taper. I would like to enter the hole that we're going into, and go about 3/4 of the way to the bottom and get tight, and then drive to the bottom. One of the things that we're not particularly interested in is a high finish. We would like for this finish to be ever so slightly rough, so that as we go into a very, very tight press, that this gives us some holding teeth. Let's make a measurement again. I am at I'm turning a taper here, and at this point about 1/8 of an inch from the end of the taper, I'm at 84 thousandths, going for about 70-ish. This piece of stock is indeed hard. I have in the tools over here some carbide tool bits, tungsten carbide bits. I use these frequently, but a tungsten carbide bit is not, definitely is not a general utility tool. There are many things that a good steel tool bit is more suitable for than the tungsten carbide. Of course, there are certain materials that requires the carbide bit for cutting. I would say that this is not the thing that I would use the tungsten carbide bit for. I'll let this tool bit run onto the stock there for a moment, a little bit back, and if that had been a carbide tool bit, it would have completely shelled the point off of it when that happened. The techniques of using the tools are entirely, of the two different types of tools, are entirely different. Now, the thing that we have here is I have overdone the cut by a bit, not by a tool bit, but by a small amount, and I'm going to saw this off and continue cutting. What I have actually done is on the smallest end here, I am about 69 thousandths of an inch in diameter. That says that that would never come down tight, even in the bottom of the hole. So I'm going to take off just a little here. I would like for this to come down tight, even right down in the bottom of that deep hole. We cut back a little. Let's touch that with a file to facilitate entry, and try again. Now I'm running tight within about 1/10 of an inch. After about 1/10 of an inch of entry, that is tight. I'm going to cut off just a little bit more. The thing that I'm gaining here in this routine is that I am measuring the mouth of the hole and then measuring as it goes deeper. Right? See what we have right on the tip. Alright, let's try in there. Alright, I'm tightening up pretty rapidly, and I want to mark the point on this that I am becoming quite tight, and I'll use that, the dimension at that point, to continue as my working dimension. Alright, let's continue on. One of the problems that we have in this technique is that you cannot be sure, you cannot be absolutely sure of your measurement, because when you're deliberately cutting a rough cut, you're measuring at the top of the burr. And I want this to be a little bit rough from the standpoint of getting the best friction interference fit in this. Try again. A little more yet. I don't need to reduce the tip diameter at all. It's further back on the body that I need my reduction. Okay. Now, I believe at this point, I'll touch this just a mite more, and we'll see if we can press this thing into place. Look at the diameter a little further downstream. Oh, I think I'll do. It's a good fit. Had trouble getting it back out there. Let's try just a mite more further down stream on this. Okay, that should do it. All right, let me cut off the camera here for a moment, and I want to get some punches that we can drive this in place. All right, we're returning here. We have the piece that the pivot will be made from. We have the tenon turned out here on the tip end, out at this region. We're going to drive that into this particular wheel here. All right, we select a hard-faced bench block, and we pick a hole in that block. We pick the hole that fits the arbor very close, and we want to drive against, right up close, the section that is the body of the pinion that passes through the wheel. Now, I'm going to drive this with a steel hammer. In some of the other tapes, I urge the use of a brass hammer. And the brass hammer, the urgency was to be kind to the punches. And I don't want to drive this until it's bent over or knocked out of shape. But I do want to drive it deep and solid into this arbor. That hammer stroke feels very firm. I suspect that I'm on the bottom of the hole right there because I'm good dead tight. Now let's see how much that we stretched this arbor. We'll measure back here in the arbor somewhere that's beyond where that we actually drilled. I'm measuring 157 and a half. Right here I'm measuring 158 and a half. The question of whether or not that I swelled that arbor in that area is one that I could not reasonably answer. Now, let's set that back into the lathe and see what we can do to get this finished up to the pivot that we're looking for. Now, it's necessary to go back into the lathe with the study rest. Let's raise the camera a bit. And get our study rest back. Well, let's cut the camera off because I have to relocate. Back on the camera, we've located a number 30 chuck that we are going to use for that. Slip the wheel into the end of the chuck, and let's see. We want to get this just as true as we can out at the point that we're going to support it, and then we will put the study rest on it. So, back onto the lathe with the study rest, As we place this on, we'll turn this to the outside rather than this because we need to get in close for this particular turning operation. Go back on here, and have to get the draw bolt tight in it. Let's select the drawbar, roll this just a little bit. We were in alignment with the lower supports on this, and now we'll let down the top support. We'll drop oil on it, see what we have here. Let's see how much we're off. Take a look, and there is ever so slight tremor, ever so slight tremor where this pivot is extended on out to this distance. Probably, I feel pretty sure that you can't see the tremor in that rod there, but our action now will be we will saw this off, and then we will machine it to the dimensions that we want to fit the plate, namely about 72 or 3/1000ths of an inch. Okay, let's cut off the excess that we have here. Let me look at the plate against this. I want to cut off just as much as we possibly can because that reduces the amount of machine stress that we have on that pivot. Get a look at the thickness of the plate over here. And this is a problem where the saw frame, it's not a depth situation, it's a length. We really need more length in the saw frame to handle this type of job. I don't know of any saw blades that are made that are longer than these, so having a longer frame wouldn't really do me any good. The sound of the sawing indicates that we're approximately passing through the pivot, or nearing passing through it. Let's just break this piece off like that. Now, let me look at this very carefully before we take the next step. That pivot is in the order of 0.010ths of an inch larger, 0.008ths of an inch, something in that order, larger than the finished diameter. We had a little problem there, had a little accident. Down on the floor, where I'm kicking my feet around, I have an outlet strip with a little switch on it that turns off the camera and whatnot. And I actually accidentally touched my toe down on that switch on the outlet strip and shut out the camera. Let's do this for the most part with a file here. This is, I believe, a number 5 cut file. And what I'm going to do is to chamfer the end of the pivot. And then I'm going to reduce its diameter ever so slightly. This file has a safe edge on it, so I can go right up against the shoulder and not damage the original shoulder on this arbor. Okay, let's try a measurement on that. I think that I'm still too large. Can't get the plate in there. Let's go a little smaller on it. Let's locate the other plate and try it. I can't get that plate there. Back onto the camera, we'll try the plate on this. And no, we can't make it. We're still too large. Still too large. So just a little more with a safe edge file. Long, straight strokes, with the safe edge running against the original arbor shoulder. We maintain the chamfer. Maintain the chamfer on the end of the pivot, and let's try there. Wrong plate, right plate. Still a little large. It would be easier, and the ultimate job would be equally good if we would simply go into that the pivot hole in that plate with a broach and touch it ever so slightly, opening that hole to fit this pivot. However, the thing I want to do is to demonstrate the job can be worked to a dimension rather than altering another piece to fit the one that we have made. Just about there. Try again. Let's go a little more than I had estimated there. We're almost at success. Now, the thing I need to do, this pivot is a little rough at this point. I need to reduce the diameter a little more and to polish it. Looking at this file, this has very smooth, safe edges. This is a number 6 cut. It is very old. This file is really more of a burnisher than it is cutting file. So let's take this. We have the smooth, safe edges so that I can go very safe. These edges have been ground on this file to make that very sharp so that we do not have a chamfer. And we go on to this with a polishing operation. And see how we are now. Okay, I want to proceed further with purely a polishing operation. I want to bring this up to a high degree of polish. going to do this with the edge of a buff stick. This particular buff stick is made of very hard oak, and this is about a 400, little over 400 grit abrasive paper. We'll put a drop of oil on it. We can get up close, and I would like here to run the RPM up considerably higher. So we move the belt back to a position that will bring this up to high speed, and we go in against this for a polish operation on this buff stick. Chamfer the end, we'll round it slightly, we'll come off and polish the end, and if my judgment is correct, this should just about bring this to a fit. Alright, we'll wipe off here just a bite on that and see what this looks like. And that looks, I believe that looks good. Let's tear down the setup and see what we have. Matter of fact, this looks such that I'm going to take the steady rest off. I believe that completes the situation. I'll have to pull out and inspect this better with a high-powered glass, and we'll see what we have. Wipe this with a oiled cloth. Let me get a high-powered eye loop. Using a 10 times pivot loop at this point. Really have a little problem finding it in that. I am looking to see how square the shoulder is. I'm looking for the polish on the shoulder of the original arbor. I'm looking for the polish on the end of the pivot itself and in the journal area of it. And I want to compare that to the polish that we have on the pivot on the other end, which is original to the movement. We'll find that they're comparable, and in finding that, let's call that completed. Let's call that completed, and there is a few tests that we should place on this following such an operation as that. It's possible that we have brought some troubles into the movement. I'm going to move the lathe over, and we'll see what we can do in this test. Find my way into the camera. All right. The first thing that I want to do is to set this this pivot in the plate like this. We were actually measuring that pivot in the wrong plate. We were measuring it in the wrong plate because we couldn't get this plate up into position because of the things that's the attachments that's on it. We had determined up earlier, though, with the drill test, with the drill shank test, we had determined that the two holes were comparable in size. Now, let's go together with this, with just these two wheels in here, just the two wheels, and drop them into place. Get the center wheel in place, this one in place. Now let's roll that train and see what we've got here. Looking at the rolling of the train. Now let's try rolling it, running on this end. Now we're running on the shoulder that's adjacent to the pivot that we have just put into the movement. Now we're running it on the opposite shoulder. We find that this is very easy to run. We can spin it from out here, even from the hour hand, which is a speed step-up situation. Let's try the end play in it. See what the end play. I'm holding the plates down on the pillars, and we do have a suitable amount of end play. We have a suitable amount of end play there. So what we find at this point is that we would call this a good job. If we look out here, we just pass through. We have just passed through. I can just feel the dimple where the pivot passes through here, which is a comparable amount to what we find on the back side. And that's the way it is for pivoting a movement. I'm going to cut off the camera and clean up some of the tools here and then be back, and let's assemble the movement back together and put it to running. I think that most clockmakers would call this a major repair. It's not a real major repair, but neither is it a minor one. But it is not all that difficult. The biggest difficulty that I have in this repivoting this movement is trying to keep my hands and my head out of the camera and get my tools together so that I can have a steady flow of the work. It is not particularly difficult. I have been doing these types of jobs for 40, 50 years, and it's just another event in the day of clockmaking. I enjoy it because it is a job that requires more than just the ordinary skill. We'll be back in a few moments. Well, we're back, and let's assemble this clock movement. I need to raise the camera just a mite. Let's assemble this clock movement, put it back to running. This is the new pivot that we put on right here. That's the new pivot on the wheel. All right, we'll go into the assembly situation as we did before, with less explanation on it, because that we have already learned to assemble the movement. Wheel to go in like this. You might try taking your watch and time some of these operations to see what it's like. In all probability, I could do a little better if I wasn't under the camera. Better, I'm meaning time-wise. If I were not under the camera and we're not discussing this at the same time. But as we drop these wheels in place, we'll see how long that it takes to bring this movement together. I'm having some trouble with the escape wheel there. I can't hit the pivot hole, and now I've dropped another one. Let's see what I've got there. I suppose I had both ends of the pivot of the escape wheel out. There we are. And let's just run a couple of nuts onto this thing now. We'll begin to pull this up together and see what we have. And a little wrench that will pull these pillars up tight again. Turn the click around to its appropriate position right here, and in goes the ratchet. have to move that over, hold down the mainspring, the mainspring arbor, and we'll latch this in place. There we go. That pretty much covers what we have to do on this side. Let's try spinning that train and see what things look like here. See this train is spinning freely. All right, let's go together with the escapement. I'd like for that train to stop turning before I start putting the escapement together. Be sure we let off about a tenth of a turn of mainspring there. Go back on the escapement anchor. We recall from right up front that we decided that we needed a visual position of this bridge to be just above the edge of the plate. I've got a problem of locating that pivot hole there. Looks like I'm going to have to get there it is. Looks like I'm going to have to get the eye loop to look in there and do that. Most of this work is done by touch. Young people do it by sight, but when you get my age, there's so much of it that really goes on by feel. All right, we'll raise this this bridge just slightly above the plate. We'll snug that up. Raise this side slightly above the plate, and we'll snug it up. And so much for that. That looks like it's approximately in beat. And what do we do here? We'll wind this up. Let's give it the one turn that we were talking about before. There's a half, and about there's a turn. Let's see what we're doing back here in the back. Let's talk about this situation a little further while we're sitting here with this ticking away. Raise this back into the camera. There we are. The job you've seen is a type of job that can be performed on a movement without degrading the plates, or without degrading the gear, the arbor, or anything in that manner. Or it could be done in a manner that would really discredit the remainder of the pieces in the movement. The best possible position that a workman can take is to do the very best job that he can on every job that he works on, whether it be a lowly antique West clocks movement or something that has very little value, or if it be the highest class movement that has ever been in the shop. The point is this: it's a matter of personal pride. Our skill is a function of our personal pride. If we lose our pride in our workmanship, our skill will deteriorate along with it. I'm going to assemble the remainder of this pendulum and hang it off the edge of the bench here, and we'll look at it for a few minutes. Let me find the pieces and we'll be back. Turn the camera back on. I've got the suspension spring back in place on this. I think what we'll do here is just take off our feet up front here, and we'll set this thing up and start it running. Incidentally, I would encourage each workman to make up a set of these type of devices. Let's see if we can get where we can see this in the light a little better. This is a little piece of brass block. It's just a clivus-like piece. It's about 5/8 an inch, 5/8 of an inch across. As a matter of fact, it's just a few thousandths less than 5/8 of an inch, and this is threaded with a headless screw. This is a square shank that was made from a square rod. It has a cross hole in it, so I can use the bench scriber in it. You can buy these things from a supply house for about a couple of dollars per foot, and they are very, very nice, very functional in the clock shop. When I made these up, I made them up with two sets of legs. The other set of legs is about an inch longer. This is the more common length that I use. Turn the movement around like this. Remember, we're wound one turn of the mainspring, which is a very, very small percentile of the winding distance, and we'll hang the pendulum on here and begin the run. Again, we'll look down here and see if we can, well, the camera doesn't reach this right at the moment. I sit on a stool for all of my work here. Let's see if we can determine about how much that's swinging. We're swinging about scant 1 1/4 inch right there at that moment. I sure would hate for this to slide off of the bench. Sure would hate for this little movement to just slip off the bench. I can't quite get the light on it there. But the point is this: work careful, work with pride. There are none of these jobs that are too difficult. Just require some thought, a little bit of tools, and a little bit of practice. And you can become very proficient. While we're talking here, in just a few moments, let's see what this is reaching now. We were a scant 1 1/4 inch, and at this point I'm about it's about 1.55 inch of swing. A very healthy swing. We have a very good recoil on the escape wheel, and this movement's taken quite a bit of work here in these clock talks in the last couple of days. We'll shut off here, and we'll come back later with continuing the Huckabee random clock talks. Let's talk about tools. Specifically, let's think in terms of a lathe, and what constitutes a good lathe for a clock shop. Well, who knows what is a good lathe? Lathe is like most other tools. No matter what you have, you ultimately find you need something else. Let's look at this little lathe that I have in my shop. I had this lathe custom manufactured by Ideal Manufacturing and Engineering Company of London in around 1961. At the time this lathe was built, it had, I purchased every accessory that IME had to offer. Everything that they listed as either standard or custom built features for the lathe. Let's take a look at it and see what we have here. The bed is a classic watchmaker's bed length. If we look, we see that it is a V-bed lathe, unlike most American watchmakers' lathes. It has a draw bolt and a shoe in the center of the bed. The fixtures that's used in this lathe does not interchange with American lathes, except in the headstock. It is 50 millimeters high in the headstock. It has the Webster Whitcomb size spindle. If we look a little further toward the rear, right in this area, it has a 1/8 horsepower motor, and this is a variable constant speed motor. That sounds like a misnomer, but what it amounts to is that you can dial in a speed, a variable speed, and then that speed is held constant while you're in operation. That is controlled by this control unit that is on the backside here. This control is made by General Radio Corporation, and the motor is made by the Bodine Electric Company, both American made. If we take a look on the controls here, this is the on-off switch, this is the forward-reverse switch, this is the speed control knob, and this switch here is a high-low range. It's like shifting into high-speed, low-speed gearing. We turn on, we have an on, a run light, and then this adjusts the speed, and whatever speed is set up there, it remains constant. If we flip the switch to the upper position, that doubles whatever speed that we have in the lathe. We leave the motor with a small leather belt, goes up the backside on step pulleys to a counter shaft, and from the counter shaft we come forward to the spindle. This gives us a large variety of step pulleys, and then the variable speed that says it can run essentially any speed that we might desire. The lathe is mounted on a kitchen cut board and on 4 heavy rubber feet. What this amounts to is that I can turn this lathe as needed for a vantage point and whatever the machine work might be. I frequently work on it from about this angle, looking right into the headstock spindle. Now let's look at some of the accessories that we have. This is a faceplate, and this faceplate is capable of chucking devices and things that have features that are not symmetrical. This has to be driven at slow speed when you're machining with, on the faceplate. And if you'll notice here, we can pull down to a very slow rate, and that rate will be constant in our machining operation. We can pull up to the faster speed. If we like, we can reverse the motor like this. There are certain operations when you work in the facing into the headstock that you may want to turn your tools around for a vantage point and then drive the motor in the opposite direction. So that's the primary advantage of the reverse switch there. Let's take off the faceplate and try another item that we have here. This is not very frequently found in the watchmaker's lathe or the clock shop. This is a 4-jaw chuck. This is a step chuck with 4 jaws, independent jaws. These are independently set up with an Allen key, and these jaws are reversible so that you can also turn around and use what is here outside as the gripper in that. See what this looks like. This is the forward direction of rotation, and we can bring the speed on up. The jaws are a little off symmetrical where they're setting now. It gives a little appearance of trimmer. All right, let's look further at an accessory here. This is a 3-jaw chuck that is well known to most workmen. That's a very nice little chuck. Let's just leave that in there and look at some of the tool holders. This is not a tool holder, this is a tool rest. This is a tip-over rest of the type that we frequently see in the watchmaker's lathe. It's a very nice tool holder. Tips over, can rotate the top, has a nice little latching handle. And here is an instrument that you rarely see on a watchmaker's lathe or any other kind. This is a saw table. This is a saw table. Let's turn it over this way and look at it. Has a T-square, has a guardrail, not a guardrail, a rip fence on it. Has the rip fence and a slot right here for the blade. You chuck up an arbor in the headstock with a saw on that arbor, a metal cutting saw or what have you, and then we can work with this saw cutting out small parts. That is tip over also. All right, let's go another one. For the tool slide, if we are working something that we want the cross slide, this is a 2-deck slide. This is longitudinal. This is cross feed on this particular unit. That slips off in a quick change fashion. Let's look at this tailstock. Tailstock has a quick lock on it. It has a lever feed. This lever feed can be turned. I usually work with lever feed from this vantage point down front. Here's the locking ring on it. It is a chuck holding tailstock with a drawbar. Being such as that, we can also use it as a drill chuck holder. We can set in a Jacobs style drill chuck that we have here and use that for drilling. I oftentimes drill in this lathe using a pad, a drill pad back here. Chuck the drill bit up front, rotate the drill bit, drill in between against the pad that is in the rear. This unit is also a very fine little wheel cutting engine. This is suitable for small clocks, large watches, possibly small watches. I've never cut wheels for small watches. Let's see how that we would use that. Let's turn the camera around this way a little. Right here is the indexing head for it. This index plate here, see if we can get in where we can see the holes in it. Well, I don't know whether we can or not. I don't seem to be able to get to see the holes in this. This index plate here has about 10 rows of holes, and they range from, I believe it's from 50 to 90 holes per row. Then there is a latch that latches this in place, and this can be indexed one or more holes as is desired and latched into place. We'll think about how to use this. There's a number of techniques in using it. The one that I use for the most part looks like this. We'll have to move out here a bit. We set this up in this manner. I have to get this draw bolt tightened up here. All right, we set up in this manner, and now we pull up underneath. Let's turn the camera so we can see that again. And this gives us, and the gibs on this is pulled up rather close because I have just been cutting a small gear on this. This moves the index head front to rear. Let's see if we can get a little better vantage point in the camera. Here we are. We can see the index head. Here is the spindle, and this slide moves that assembly front to rear. This slide down here moves the assembly left to right. This slide here raises, we're raising the gear cutting assembly. Now the process of using this is to go into this spindle. This is a Webster Whitcomb spindle here with a drawbar. We go into this spindle with an arbor, and we have our gear blank placed on that arbor. Then in the headstock we have a second arbor in here, standing out approximately this far, not quite this far, that has the gear cutter, it is the profile gear cutter, on that arbor. Now, we pull up into the region that our gear blank is horizontal. It's lying horizontal here in front of the saw. And here we pull in the depth of the cut that we're to make, and we crank down, and we carry the blank that is to be cut through the saw, which is carried in the headstock, that saw being a profile gear cutter. The usual mode of operation is to have your gear blank below the saw. The gear blank is below the center of the saw, and we adjust the positions here, this for the depth and this for the central axis. Now as we start the motor, we crank, we pull up. The gear cutter is cutting down, throws the chips down. We make the pass through the gear blank. We go back down, pull the index pin and rotate, pull the index pin and rotate to the next index position. The next index position may be a single hole or a multiplicity of holes, and we make the next cut. We progress in that method until we have completely passed around the gear. So we find in this this instrument that we have a full-fledged wheel cutting engine. We have the full-fledged lathe with all of the handheld watchmaker type graver tools that we use. We have the cross slides both directions, and the tool post. I don't have the tool post in hand, but we have a tool post that mounts here, so we have that facility. We come down to this, which is a lever tailstock, and in addition to that we have the tailstock here, which is a micrometer feed tailstock, also holding collet holding. And in this there's a micrometer barrel. You can use this for controlled depth of press, though I have never used this as such. This is also recommended as a jeweling press for watches. I think that it would be a little cumbersome to use, because that in a jeweling press you really need to press down where you can look down into what's going on. But it has many, many features. These draw spindles will remove out of this tailstock, and we have in that dead center runners. We have a pair of spindles that we can put in here and run this as a dead center lathe as the English turns, which is the most accurate of all known lathes, has the highest accuracy capability. As we think a little further in this, also have the hollow runners that goes in here, and the pivoting attachments, that is the offset, the offset cup female centers that goes in here, and the through drilling for pivoting. We've just finished doing a pivoting job on this tape, a little earlier on this tape, and we could have drilled, we could have caught this and drilled and done that pivoting job in about 1/2 the time on this lathe that we did on the tape previously. The reason I did not do that, the lathes that you find among the craftsmen that have the capability of this are just extremely rare. So it really wouldn't be of much value to teach someone to use something that they possibly would never own. Now this is what the a custom built lathe and custom features can look like and what it can do for you. I bought a pair of these lathes in about 1961, I believe it was, and they're identical, and I have one set of tools for them. I do not have the two sets of tools. I have two tailstocks, I have two headstocks, those types of things. I have two sets of tip-over tool rest of this type, but I do not have two of everything that is here. The major pieces, I only have one. The other lathe has a bed that is 18 inches long. You notice that when we get in here, we're pretty much out of space in this area in the watchmaker's lathe. We can't handle this tailstock, this headstock, this tool slide all simultaneously. They have to be used piecemeal and more carefully chosen on the job. The other lathe is identical to this, except it is 18 inches long, and instead of the single pedestal, which this one has, it has a pair of pedestals under it. It's a very strong lathe, it's a very good lathe, and it can turn out some excellent work. Subsequently, we'll talk about the other lathe on some tapes, and I have some carbide tooled pivot grinding equipment that is custom built, that I think that is very unique in the industry, and at a later time we will show that also. The other lathe with the 18-inch bed has an identical drive motor. It has the same general radio control, it has the same Bodine motor, and this is a very powerful motor, a very very well controlled motor. The ability to run this from just almost zero speed, right here you can see that it's running very slow up to very high speeds. This motor and this drive system is the quietest, or the pair that uses this system has the quietest, the smoothest, and the most powerful motors of the lathes that I have in the shop. This is an unusual story that goes as to the way that I got a hold of these lathes. I found a textbook somewhere once. It was published by the National Association of Goldsmiths of London. It had an ad in it for IME that says they would custom build clockmaker, watchmaker, industrial small tools. I got in touch with them, and they said, sure, we'll build you anything you want. Just send us a sketch. We'll build you anything you want. They'll quote on it, and I did, and they did. But in that period of time, I suppose even more so than now, there was a world scramble for gold. At that period of time, the United States government guaranteed dollars in gold that were spent abroad. The array of the two lathes and the array of tools which I purchased, they quoted me at a little over 22 ounces of gold. The 22 ounces of gold at that period of time was at about $45 an ounce. I believe that come to about $1,000 in round numbers for the whole array, for everything that was there. Okay, I says, build it for me. They said, oh, no, you have to pay us up front. Well, who wants to pay some foreign manufacturer money up front to build you something? Well, an agreement was worked out that the 22 ounces of gold would be deposited to the account of IME in London, would be deposited in a London bank, and they would build the tools, and when they delivered shipping documents to that bank showing that this was shipped, that they would that the money would be released to them. Well, these fellows didn't work much faster than well, they just didn't work very fast. I waited almost 18 months for these tools to be finished, and I really thought that my 22 ounces of gold was gone forever. One day I got the notice We've worked hard. We've got your tools finished. They've been shipped. We've got our money. Goodbye. And these were shipped by, I suppose, sailboat or something that required about 3 months for them to arrive in an American port. When they arrived in the American port, I got another surprise in my life. I had an import duty taxed on to me for about $600. So I paid 22 ounces of gold and about 600 American dollars to get these tools delivered to me, 1961 or $62. And the tools are some of the finest that I've ever seen in anyone's shop. But imagine in 1987 what 22 ounces of gold would be to buy tools for a clockmaker's shop. I'm certainly glad I bought them when I did, and as we continue some of these tapes, we will talk from time to time and see some work done on these machines. There's some real eye-opener jobs that we can perform on these. I've had them now since '61, that's about 25 years I suppose, and they have served me well. I've earned many dollars. As someone has said about something that was old, I once heard a person say, "It doesn't owe me anything now." These tools don't owe me anything, but I'm still very proud of them. As time goes on in these Huckabee clock talks, we'll use some of these before your eyes, and you'll see how they work. I would highly recommend the quality of the IME tools. I have no idea what the cost structure would be today, but they're extremely fine tools.